Hello dear people interested in robotics, welcome to our research video row. Today, in this video, we want to address a topic which at the first sight resembles an extraordinary fantasy vision and yet is fascinatingly practical. We'll explain what an artificial multifunctional interconnected vascular system is, how it works, and most importantly, which new possibilities it enables. As you can imagine, biological multifunctional systems and their benefits are usually one of the most significant differences between living beings and robots. They're coming together with many useful abilities, such as enabling a self-generating and reproducing energy system, or forming autonomous systems which are able to grow, or creating density between supplying and operating components with a flawless interaction and intertwinement without standing in each other's ways, or conflicting during external influences. Or being an interconnected circulatory system which is not only able to extract and store energy, but also uses its connections for multifunctional purposes. Sure, you could compare the currently most common system of typical robots composed of isolated units, each with its own individual purpose and optimized for specific tasks, to animals with the explanation that they also have various body parts, with each having one specific purpose. For example, the legs are used for walking, and the eyes for seeing, and so on. But this doesn't describe properly the functionalities of a multifunctional interconnected system. As the term multifunctional reveals, the viewed system needs to have a practical interconnection between multiple functions. The best example for that is the human circulatory system. Not only it transports oxygen and nutrients through the body, but also it regulates internal body temperature and helps to get rid of waste products, and is an important factor when it comes to preventing and fighting diseases. A group of 4 American scientists managed to demonstrate how practical an electrolytic vascular system works and its efficiency by building a lionfish-inspired aquatic soft robot. Its construction comprises a synthetic vascular circulation system containing coherent zinc-iodide flow cell batteries that supply the power to pumps inside the fish and electronics through electrochemical redox reactions. While functioning, the flowing and pulsating liquid half cell of the battery contributes to the mechanical movement of the fish. Movement means both for traveling and fanning its pectoral fins, one of the methods that lionfish use to communicate. As you can tell, those batteries don't induce the problem of occupying necessary space inside the robot or additional restricting weight. On the contrary, the circulatory system combines the functions of hydraulic force transmission, actuation and energy storage into one construct, which results in longer durations and a better space use management. The energy storage mechanism is modeled after the redox flow batteries, which contain a liquid catholyte. The circulation of the liquid catholyte is key for the energy distribution and fills according to the direction where the fish needs to go the corresponding fin. The fish has a microcontroller inside for activating the right pump and the decision which fin has to be filled with robotic blood. The red traces show where the blood flows. As we can see, in the lowest picture the side with more blood expands and bends the fin. Having a look on a peristaltic pump, moving the catholyte from the dorsal fins to the pectoral fins. It reminds us of the natural cardiovascular system. The pump resembles the heart and the red fluid looks just like blood. The robotic fish has a tail fin and 3 sets of side fins, 2 pectoral, 2 pelvic and 5 dorsal fins for a good direction control. Also, the fins are flexible and soft, allowing good bending, and consist of convenient price material. Furthermore, hydraulic fluid energy storage allows autonomy, efficiency and a higher energy density. As we already found out, the usage of electrolytic vascular systems for energy has a lot of advantages. The biggest advantage is the closing of gap in efficiency, mobility and a growing congruence to actual living beings. Since the beginning of human existence, generations of scientists and engineers aim for designing the most lifelike machine. And in our opinion, implementing an artificial cardiovascular system is a big step in the right direction. If you're interested in further lifelike robots, especially in humanoid robots, you should definitely check out Roboy.
The Roboy project is an open source project with the goal to build a robot as good as the human body. We created an open platform for robot development that unites researchers, companies, students and artists from a broad spectrum of disciplines. Roboy means full-stack robotics, from mechanics to electronics to control to cognitive systems. Artificial intelligence is everywhere, and we work on all levels to make Roboy truly intelligent. The Roboy team aims to build better, more useful robots by adopting principles from biology and to help humans with musculoskeletal limitations through better prosthetics, better training, and exoskeletons. So if you are interested and want to know more, check out our website roboy.org or the GitHub account github.com/roboy. Thanks for watching another episode of R-Cube. See you soon and stay curious!